we're going to look at the concentration, not just of the whole compound, but rather the concentration of individual ions in our compound. And these two values are really related pretty well. Okay, so let's review what we know about concentration. Before we even get too far into this, let's review concentration. Okay, when a compound dissolves in water, remember water kind of picks off parts of that compound. Do we remember that little video we watched? Water kind of takes an ion, surrounds it, and pulls it apart. And so what we're looking at here is now we're going to start finding what's the concentration of an individual ion in the actual solution. Okay? Question here. The first question says, give the concentration of each ion in the following solution. And if my solution is 0.5 molar, and then what's the name of that molecule? Can you name that first? Cobalt nitrate, almost, but what am I missing? Cobalt 2 nitrate. That's tricky because cobalt's got a Roman numeral. So if you weren't looking, you might not remember that one, but that's okay. Cobalt 2 nitrate. So I want the concentration of each ion in the solution. And the way I do that is I look at what's the ratio of the ion to the whole part. Okay, so cobalt 2 nitrate looks like this. So if it would ionize, do you know what I mean when I say ionize? If it would ionize, if it's going to break apart into its ions, what would it form? We would have a CO molecule that has a charge of +2. And what else would it form? Okay, it would have a nitrate ion. How many of those nitrate ions? It would have 2 of them. Okay, so if it were going to ionize, this is what we would be left with. Cobalt, nitrate, nitrate. Do we agree with that? Right, and we know that because there's a 2 right here. That tells me I have 2 nitrate molecules found in that whole complex molecule. So if it were going to dissolve or ionize, it would break apart basically into 3 different ions. Okay? And so now what we're going to look at is the ratio of what's the part as compared to the whole. Right? If the whole thing has a concentration of 0.5 molar, 0.50 molar, what does the concentration of cobalt ions have to also be? Would it be the same or would it be different as compared to our entire molecule? It would be the same because for every molecule of cobalt nitrate, there would be 1 cobalt ion, right? The ratio there is 1 to 1. So my concentration would be the same. So this would be still 0.50 molar. What would the concentration of nitrate ions be? Would it be the same? Would it be twice as concentrated or would it be half as concentrated? What do we think? It would be twice as concentrated because there's double the amount of nitrates as there are cobalts. Would we agree with that? So we're going to take our concentration and we're just going to multiply it by the ratio. So our concentration of nitrate ions would actually be 1.0 molar. So all we're doing really here is looking at the ratios. You could do a whole bunch of math to go through and prove this, right? We could find out how many moles of nitrate ions there are per that liter or per that volume, but the math is going to come out the same. You're essentially just looking at the ratio of the ion as compared to the whole, right? If it's a 1-to-1 ratio, then our concentration is the same. 0.50 molar cobalt and 1.0 molar nitrate. Right? Because in our compound, when they break apart, there is twice as many nitrate ions as there are cobalt ions. Do we agree with that? Because there's 2 nitrates for every 1 cobalt. Okay, I want to make sure we understand kind of the big picture of what that looks like. Does that feel comfortable? I mean, it's simple math once we kind of look at it, but we got to make sure. What's my variable and my unit for concentration? Molarity, right? And molarity is given with a capital M, right? Molarity is equal to what over what? Moles of our solute over liters of our total solution. So we're able to calculate how many moles of this certain compound are found in a certain volume of our substance. the higher the molarity, that means the more of those things per liter, right? We've got a greater ratio of our solute to solvent, right? That's really what we're looking at here. Okay, and so when we look now at concentrations of individual ions, we need to remember what happens in the dissolving process and in the solution process. So let's go back and we start looking at, understand how we're breaking that down, okay? Give the concentration of each ion in the following solution. We have a solution that's 1 molar, and then what would be the name of that molecule? Iron 3. And then this one's actually, I don't know if you have this one in your box. This one's actually called perchlorate. We might not know that one. You know how we go 8 to 8 is subtract 1 oxygen? If we want to go up 1 oxygen from 8, it's called per something 8, right? That's not really a pattern that we looked at, but that would be the name of this one. So this would be iron 3 perchlorate, which I wouldn't have to have you do that yet. But okay, so what's it going to break into? We need to figure out what's our compound going to ionize to? It's going to form what? How many iron atoms would we have? One of them, and its charge would be +3. And then we would have chlorate, or perchlorate, I apologize, perchlorate molecules, and how many of them would we have?
3.
We have 3 of them. Okay, you can either write them out individually if you want, but I just know I'm going to have 3 of them based on this ratio right here, right? 3 of them. So when it ionizes, I have 1 iron and 3 perchlorates. And so what would be the concentration of iron?
Triple.
Of just iron?
1.0.
Just 1.0 because it's the same, right? It's 1 iron per big molecule. And so then for perchlorate, what would our concentration be? 3.0 molar for perchlorate, right? Because we're going to take our concentration of our total times 3 because there are 3 times as many perchlorate ions in there as there are iron. Okay, so here are our 2 concentrations. This is for iron and all that kind of stuff. Does this charge make a difference for us when we're looking at the ratio? The charge itself makes no difference, right? So that's not the ratio we're looking at here. We are looking at the ratio of ions to one another. Okay, so when we're given the concentration of our total solution, it's very simple, right? We're just really looking at our ratio. Calculate the number of moles of chloride ions if we have this concentration and this solution. Okay, so we're going to take this sample solution and we want to know the moles of just chloride ions, okay? So what do you think our process maybe should be first? There's a couple different ways we can go about this. Okay, a couple different ways we could go about it. You can do it 2 ways, and I'll show you both. Okay, I'll show you option 1 and option 2. They both make the sense. They make the same amount of sense. It's just that we're doing them in a different order, right? The first thing I could do is I could find moles of my total compound. So let's do that. So I would take concentration 1.0 or 1, I guess, just 1 times 10 to the negative 3 equals moles of ZnCl2 over liters, right? And I'm going to find out how many moles of my total compound are present. Okay, so 1.75 times 1 to the negative 3. And I get 0.00175 moles of ZnCl2. Okay, but that's not moles of just chloride, that's moles of my whole compound. And so from there, I'm just looking at, well, what's the ratio of moles of chloride to moles of my total? And so I could go like a little mole ratio step here, if I wanted to. Moles of ZnCl2 to moles of just Cl. And my ratio here would be 1 to what? 2, right? Because there's 2 times as many chlorides per molecule, right? And you don't have to write it in the chart if you don't want to, right? We can see that ratio happening. And so I can just take that times 2, and I get 0.0035 moles of chloride. Okay, so all I did was found moles of my total, and then I compared that to my ratio. The other way I could have gone about it is by changing my concentration first. 1 times 10 to the negative 3 molar of ZnCl2. We know automatically chloride's concentration is going to be twice that. So that would mean that chloride would have a concentration of 0.002 molar equals moles of chloride over 1.75 liters. So I can do the same thing, just really in a different order. Right? Does that kind of make sense? I could adjust the concentration first and then find moles, or I can find moles and then adjust due to the ratio. It makes no difference which of these methods you use. Right? Does that kind of make sense? So you can choose which one works best for you. They both give us the same answer. The first one, I found moles and then I attacked the ratio. This one, I attacked the ratio first and then I looked at my concentration in moles. It doesn't matter the order that you solve it in. Okay, whichever way you prefer. Why don't you try the next one here on your own? The typical blood serum is 0.14 molar NaCl. What volume of blood would contain 1 milligram of NaCl? So this one's not even a concentration of ions practice. This is just a regular concentration practice. Okay, so why don't you try this one on your own? Did we remember how many milligrams is in a gram? Maybe? 1,000, right? 1,000. Okay, so using this top conversion, I was able to find out how many moles of NaCl would be found in 1 milligram. And from there, I can say my concentration is 0.14 molar equals 1.71 times 10 to the negative 5th over liters. Do you remember our shortcut here when we're trying to solve for the variable on the bottom? No, we're not going to multiply them. We need to switch them spots. Right? I need to get liters by itself in the numerator. So in order to do that, I've got to move liters to the other side, divide over that 0.14, which is the result, the result of that is the same as me switching them spots. So when I do that, I got about so I got a really small number of liters, 1.22 times 10 to the negative 4th liters, or I put it into a regular number, or I could write that out in milliliters. That would give me a little bit of a better picture of that, 0.12 milliliters, or I could say 122 microliters if I wanted to, right? We can go all the way down to give ourselves manageable numbers there, but it didn't ask for a particular volume unit, so we could have taken either of those answers. Okay, questions about that one? Do we see how that walked through? Called dilutions. Do you know what it means to dilute something? What's like the standard phrase for when I'm diluting something? What am I doing? Yep, I'm watering it down. Right? I'm just putting more water into it, or whatever your solvent is, but most of the time it's water, okay? So in chemistry, we typically deal with what are called stock solutions, and stock solutions are things that are made in a lab, or solutions that are made in a lab to a really, really exact degree of precision. Like they're very much exact, okay? And so those might be high concentration solutions that we buy, right? In my lab, I've got solutions in my cabinet that are anywhere from 18 molar down to 1 molar, right? And in our lab, we want to work with things between like 0.1 molar and 1 molar, right? We don't want things super concentrated because we can still see the chemistry but not use a super concentrated or dangerous solution, right? If I'm working with acids or bases, a really high concentration of that could end up being dangerous. But if I water it down, I still see the same chemical properties and I still see the chemistry play out, but I can do it in a safer way. So I take these stock solutions and I basically water them down to the appropriate level of concentration that I want, okay? And so we use this equation right here. C1V1 equals C2V2. All right, and this C stands for concentration, and V stands for, what do you think? Volume, right? Concentration of the first times volume of the first equals concentration of the second times volume of the second. Sometimes you will see it like this. M1V1 equals M2V2. This just means molarity, right, which is still just the concentration unit. So it's the same equation. Some people just write it that way. That's not how I learned it, and this is not typically how I use it, but we're looking at the same thing. Concentration times volume equals concentration times volume. And so what we're doing essentially is setting up a proportion, but in a non-fraction, right? We're looking at ratio and proportion. So, yeah, let's look at some problems here and how we would apply this, okay? We need 500 milliliters of a 1 molar acetic acid solution from a 17.4 molar stock solution. What volume of stock solution is required? Okay, so let's envision what we need here. We're trying to make 500 milliliters of a solution that is only 1 molar. Okay, so these things have to go together, right? We agree when we put them into our equation, C1V1 equals C2V2. I don't really care which set of variables are the ones or the twos, right? The before and the after. I don't really care as long as we're consistent and we pair the right things together, right? My goal is to have 500 milliliters of a 1 molar solution. And then it asks me what volume of this 17.4 molar solution do I need to be able to get there? What would you give me just some thoughts on how much of that 17.4 molar solution are we going to need? A lot or a little, do we think? We're not really sure yet, but think about how much I want to water that down. I want to take it from 17.4 all the way down to 1 molar. So I'm gonna only probably use a little bit of that stock solution, and the rest of my solution will be water, and then it'll get me to the concentration that I want. Okay, so the way I set it up is this. In this equation, you can use milliliters or liters as long as they're the same on both sides of your equation. So as long as it's consistent, you can keep things in milliliters, okay? Because it would just be like me dividing by 1,000 on both sides, right? I don't have to do that. So I'm just going to go ahead and keep it at 500 milliliters times 1 molar. So C1V1 equals C2 times V2. Now, what unit will V2 come out in? What will be my unit when I get my answer here? It will have to be milliliters because I left my original volume in milliliters. Okay, so let's just go ahead and run the math. 500 times 1, which, why did I even plug that into my calculator? Okay, divided by 17.4. I get V2 to equal 28.74 milliliters. So I only need, right, if I'm making 500 milliliters of my new solution, only 28 of those milliliters is acetic acid, and the rest of it is water. And so now I've got this much more watered down version of acetic acid that I can work with. Okay, does that kind of make sense, how we work that out? C1V1 equals C2V2. We have to read our problem very carefully and use context clues to pair the correct two sides of our equations, right? Which ones go together and which ones don't. Okay. Are we good on the math there? It's usually very simple, right? Algebra, solve for the variable. All right, why don't you try this one on your own? Try this one on your own. What's the minimum volume of a 2 molar NaOH solution needed to make 150 mils of a 0.8 molar solution? So we're kind of looking at the same process here. That solution, so 2 molar times V1 equals 0.8 molar times 150 milliliters. And so I actually need 60 mils of my stock solution here to help me make that. Right, we're going to use a little bit bigger of that stock solution to be able to find that, to be able to make that new one, right? We're not diluting it very much. We're going from 2 to 0.8, so it's not a real drastic dilution. And when that's the case, we'll use more of that, right? Can we see how that applies? Okay.